Hello and welcome everyone to another edition of the Sheffield Machine Learning Seminar Series. I'm your host Aditya Gilra, a lecturer that is an assistant professor at the Machine Learning Group at the University of Sheffield. And I'm very pleased to welcome Dr. Alexandra Sasha Luccioni from the University of Montreal. I'll just introduce her. She's originally from Russia. She did her bachelor's and master's in Paris at the Université Sorbonne Nouvelle and École Normale Supérieure. And then after that, she did her PhD at the Université du Québec à Montréal. This was in AI and e-learning to create an intelligent tutoring system. And then she has worked for 2 years at Nuance Communications and Morgan Stanley. And then from early 2019, she has been a postdoctoral researcher at the University of Montreal and Mila, which is the Quebec Institute for Learning Algorithms, working with Yoshua Bengio. She works on AI for humanity, and she's written some interesting papers on this topic, a very, let's say, popular or rather influential one, which she'll talk about also. And so the floor is yours, Sasha.
Thank you, Aditya. I'll just share my screen. So hello, everyone, and thank you for having me here. The topic of my talk today is machine learning as a tool for positive impact. I broadly work at the nexus of AI and social good, as it's called sometimes, or at Mila we call it AI for humanity. I work on a lot of different projects, but I thought that today I could talk to you specifically about the projects that I work on related to climate change, because it's a topic that I hold very, very dear to my heart, and because there's actually a lot of interesting research to be done from a machine learning perspective in this area. So to give you some context, as Aditya mentioned, we wrote a paper in the middle of mid last year, called Tackling Climate Change with Machine Learning. As you see, there's a bunch of authors, myself included, but also Yoshua Bengio, Andrew Ng, Demis Hassabis. So the idea of this paper was to essentially paint a broad picture about all the ways in which machine learning can help tackle climate change. And the reason why there's so many authors is also because there's so many opportunities. And so we split up the work. We had chapters about different topics. I wrote both the education section and the finance section, given my background and experience. And we also worked together on the general scoping, the introduction and conclusion. So it was definitely an interesting experience. And after the paper came out, some of the authors of the paper also created an organization called Climate Change AI. And essentially we work in continuing the momentum. So a paper is good, but action is kind of what we're aiming towards. So if this is something that interests you, you can go to our website and find out more about. We organize events, we do all sorts of content curation, et cetera, et cetera. But coming back to tackling climate change with machine learning, what we did is we talked to a lot of people. We talked to a lot of people working in this field, and we tried to identify impactful applications and themes. Things like individual action, solar geoengineering, electricity, transportation, city planning, et cetera, et cetera. So we identified these broad topics, and within each topic, we also had concrete action opportunities, such as, for example, understanding personal carbon footprints, understanding improving aerosols, et cetera, et cetera. And based on these, we tried to tag them as high leverage, long-term, uncertain impact, et cetera. So the idea was to help people understand the scope of things that need to be done and to figure out where they stand. And from a technical perspective, what we tried to do is create, essentially we called it a menu for action. So depending on people's backgrounds, be it computer vision, time series, reinforcement learning, NLP, et cetera, we identified where they coincide with these different application areas that we identified. So electricity, transportation, buildings, industry, farm and forest, CO2 removal, climate protection, societal impacts, solar geoengineering, tools for individuals, tool for society, education, and finance. So the idea was, no matter what someone's background is in, no matter what they're interested in, it could help them find a way to use their skills for good, in the fight against climate change. And that's essentially what happened. In my case, 2 years ago, I was working in finance, and then I realized that machine learning is kind of a Swiss knife, and I had already kind of learned in my first job more speech processing techniques and things like that. And then in my second job, financial background and financial functioning and information. And so I realized that essentially it's good to work in a field that is interesting, but it's also important for me personally to work in an impactful field. So this is why I kind of quit my job at Morgan Stanley. I joined Mila and have been working on this for the last couple of years. And I guess kind of the moral of the story is that we often think that we're machine learning researchers and we work on machine learning, but there's actually all these different things that we can apply machine learning for. And I'm going to give you a few examples today, just kind of to whet your appetite. So how can AI help in this general field? I'll give you 3 examples of projects that I work on. The first one is using computer vision techniques. It's called, broadly speaking, eButterfly. The second one is using generative networks or GANs. It's visualizing climate. Originally, that's kind of my background, and so it's called Climate QA. So I'll start with eButterfly, or colloquially called eButterfly, but the full name is Using Spatiotemporal Features for Butterfly Classification. So I'm working on this project with David Rolnick and Marta Screta at Mila, McGill, and University of Toronto and Montreal. So I guess the motivation for this project is that something we don't think about a lot is that butterflies are actually heavily impacted by climate change. It might be a kind of a small portion of the things we see, and this is actually one of the problems with climate change is that we see kind of the big things, but we miss out on the small things, such as insects, ecosystems, things like that, because they're kind of subtle, right? And so actually, butterflies are very impacted by climate change because their habitats change, because they're very sensitive to temperature and weather. Maybe you've heard about monarch butterflies that are heavily impacted because they migrate, and so changing temperatures really can make their numbers go down. And so they're linked to the ecosystem, and they're also the predators, and the plants that they pollinate are also impacted. So it's kind of this intricate web of influence. And so we decided to do our part, essentially, and we're working with a project called eButterfly that actually has existed for several years already. And the idea is to use citizen science, which is, you and me and your neighbors and your friends, in order to help figure out how butterflies essentially are being impacted, how their populations are evolving, whether there's more or less in a certain year. So essentially, typically, if it's only scientists who are doing this work, it's really, really hard because, there's only so many specialists that you can send out into the field that will make observations and then come back and then log them, right? There's not an infinite number of climate or butterfly specialists. So the idea is to use citizens in order to take pictures in your backyard, in the forest that you go for a hike, and then to submit them on this website. And then you can propose what you think it is. So I see this butterfly, I think it's X, and then actually it gets validated by experts who say, no, actually this is another type of butterfly. And you also log where you saw it, so the GPS coordinates and the date and the time. So eButterfly, we contacted them and they said, yeah, well, it's a great website and it's working well. We have 400,000 observations, but it's really it's really difficult to label images by hand. And we're like, well, we can use machine learning. But it turns out that using images alone is actually pretty difficult for butterfly classification because first of all, they're pretty small, right, by definition, and also because there's a lot of kind of butterflies that look very alike, and especially depending on the angle of the photo, obviously they're mostly not professional photographs, so they can be really hard to distinguish. So for example, these two butterfly species are actually very different, but depending on the angle and the shadow and things like that, they can be confused. And so we trained an original model just on the images, and it did fairly well. In the 80s, in terms of accuracy. But then we realized that we kind of hit a ceiling in terms of how much we can improve our model based on images alone. And we did all sorts of different approaches. We tried to segment the butterfly and ignore the background. We tried to do hierarchical labeling to figure out the species and then the genus and things like that. But finally, we kind of hit a wall. And then we realized that actually when specialists do this kind of classification, they'll not only look at the image, they'll also look at where the image was taken, when the image was taken. So these two things are actually really, really important. And why? Because these two butterflies, for example, have very different ranges. So for example, the top one is mostly East Coast North America, and the bottom one is mostly West Coast North America. So for example, if you have a photo that can be very confusing in terms of the visual aspect, just using the geographical location can really help distinguish between the two species. And actually, other species, for example, will migrate or move. So you can also use the date, knowing that this is June, this is probably this butterfly. And also there's ecosystems that butterflies will live in. Some of them will be more alpine, some of them will be more forest, et cetera, et cetera. So we thought, why don't we use all of this information in order to help guide our model? And so there's actually some related work on this. So typically what's done is that networks are trained on images and for example, geographical coordinates together. So, and they're kind of part of the same data point. So you can't have an image without spatial temporal information and vice versa. So it's actually like two parts of the main of a half. And so this has been actually like used in the literature. There's also been Bayesian approaches, which train the model separately and then combine them at test time, essentially kind of helping figure out what the probability is based on both. And of course, there's image-only classifiers that actually are trained on ImageNet or et cetera that do fairly well, once again, but they hit a wall in terms of certain species. And so our idea was that at train time, what we do is we take an image, we run it through what's called a ResNet. It's essentially a pretty deep neural network, convolutional neural network. And then we have a probability of whether this image belongs to a species. And then we add other spatial temporal features such as the latitude, the longitude, and the date, which essentially we run through a sine and cosine functions because we want it to wrap around. Because I mean, first of all, the Earth is a sphere, and also because dates, we want for example, 31st of December and the 1st of January to be one beside each other. So we don't want it to be just like a flat structure. We want it to be circular. And then we encode them in another neural network architecture, and then we have another probability. So essentially, we have these two probabilities of whether the image is a species and whether this set of spatial temporal features belongs to a species. And during test time, what we do is we have a new image, and then we run the image and the spatial temporal information through these two networks separately, and then we combine them. And essentially, what we do is we redistribute the features from the image network using the spatio-temporal probabilities, saying that, well, maybe these two species are visually very similar, and so the image network can confuse them. But the spatio-temporal network knows that this species is more likely to be at this point in time in this place. So we redistribute and say, okay, instead of this species is going to be the species that has a more probable location. So essentially, we redistribute the probabilities. And so what we've been tracking is we've been comparing. So this is a work in progress. Definitely, it's not a done deal. But essentially, we found that this approach improves on the image only approach. So we have, if you see in the middle column, it's just the image, and then the second column, the last column on the right, is the image plus the latitude, the spatio-temporal features essentially put together. And we see that it does improve results in all cases. And what we're tracking is both micro accuracy, so it's just like the average total, the total correct, like gross total over the gross total of samples. And we have also the macro accuracy because it's per species, because we have some species that have very little samples. So we want to make sure that we cover both essentially. And so that's why we have like top 1 micro is like the overall, and top 1 macro is per species, which is harder because there are some species, for example, that will have 30% accuracy, even if like the overall accuracy is 85 or 86%. So we're tracking both of them, and we're trying to essentially make these numbers go up, because the idea is to replace or actually reduce the number of human interventions needed for eButterfly. And so we actually are currently deploying a system already on the platform that will recommend species, like 5 species or 3 species, depending on how certain it is. So when someone uploads a new image, it doesn't have to go through like human validation because they're just overwhelmed with these validations, that it can go through a neural network instead. And then essentially the idea is to keep training it, to keep improving it, and to assign scores to certain people. Like when they've achieved an expert score, they've gotten all the species correctly by themselves. They don't need interventions anymore. It's to have a bit of a smarter system to help make citizen science a bit more user-friendly. But we're also working to improve our model. So that's kind of like the application side, is that we're deploying a system, but we're also working to improve our model for example, augmenting rare species, because we see that their accuracy is very low. We're also trying to test on other species of birds and other insects to see if the same kind of approach works. And of course, the deploying on the eButterfly website should be happening in the next couple of weeks, so that we can test out our system and see how robust it is, and see essentially, initially it's going to be the humans are still going to be in the loop, and then a system is going to be in the loop, and we're going to compare the two. And then if we see that really the answers are very coherent, then we can kind of let the scientist rest, and kind of only ask for their help when essentially the probability assigned by the system is very low. So when the system says, I really don't know, then we can ask for a human intervention. But if the system is 100% sure it's in Monarch, then maybe we don't need to bother the entomologists. So that's the first project that I'm working on. That's really interesting and kind of hopefully impactful, because citizen science is a important thing. The second project that I'm working on with lots of people, including Joshua Bengio, my supervisor, Victor Schmidt, who's another student on the project, essentially it involves visualizing climate change. So it's kind of a different approach than citizen science, because it's an awareness raising approach using AI. So it's kind of a new project in that sense. So historically, climate change it's been an issue around which it's hard to mobilize collective action. So this is something that's been picked up on by behavioral scientists and psychologists. And they study this phenomenon, and they realize that, the typical IPCC reports of 1.5 degrees warming and kind of the curves that they show, and it's just too abstract for a lot of people, because first of all, the language is complex, because the charts that they show can be very hard to understand, and the language is also very, scientific, right? You're trying to say things in a way that's really represents only the data and not kind of the impacts that it has on humans. So they'll say, well, the ice is melting, but they won't say cities will get flooded and things like that. So it's really it's a way of communicating, but that will communicate the information without the risks. And so there's researchers who are studying climate risk communication, and they observed that the most impactful messages around climate risk communications are ones that are more emotionally charged, so that use kind of stronger words, and personally relevant. So people will tend to listen to messages that they think will affect them. So if the Miami is going to be underwater, I don't really care. I don't live there. But if it's, the sea is rising and my neighborhood is going to be flooded, that's something that people tend to care about. And they also discovered that images in particular are a big part of the equation, because they essentially permit communicating information more seamlessly and kind of quicker, right? And despite this, scientific communication is kind of still the way it is. It hasn't changed much. And so there has been this typical kind of, it's called the intention-action gap in the literature. So a lot of people care about climate change. A lot of people want to do things about climate change, but few people do things about climate change. And so typically they've done surveys and studies that say, 95% or 90% of people are aware of climate change, that it's an issue, and believe that it's an issue. But only 40% or 50% actually take individual actions in order to mitigate their impact. So there's this kind of big enigma of how do we help people bridge the gap, the intention-action gap. And so we're developing a tool that should be ready in a few months, hopefully, that uses AI to kind of raise awareness with regards to climate change impact. So based on this literature, we're like, well, what if we make images that are both more personally relevant, but with remaining kind of scientific and based on existing events? And so climate-related extreme events are getting more and more frequent. It can be floods, wildfires, as we've seen this last year. Smog is impacting people worldwide. But, proportionally speaking, it's always in places that are far away from us. California, Siberia, I don't know, India, like it's always far away. So people typically think it's someone else's problem. And our idea is, what if we brought it home and help people realize that it's actually a global problem, just maybe not now in 2020, but in 2030 and 2040, this is going to become everyone's problem, and essentially by that time it's going to be too late to take action, or it's better to take action now in any case, because things will happen in the future. So our idea is to kind of help people time travel and space travel, and to see what would happen if the events happen in their own backyard. And to do this, we use Google Street View and these networks called GANs in order to transform images and create this kind of time travel effect. And essentially, our goal is both to raise awareness, but also create empathy and to change behavior. Ultimately, the idea is people will change their behaviors. And so what we're doing is kind of a two-step generative approach. So, for example, if we start with the flooding phenomenon, we realize that there's actually two parts of it. There's generating a kind of a mask, what we call a mask of where the water should go, and then generating the water on this mask. And so essentially it's a two-step approach because it doesn't affect the whole image. It only affects a part of the image depending on how high the flooding is. But there's always the sky is going to be the sky, and the roof can be the roof if it doesn't go that high. So the idea is we created a two-step generative approach to leave buildings and sky intact. And actually what we realized quite early in the project is that there's not a lot of data. There's not a lot of real images of flooding from a first-person perspective, because that's what we really need. We really need as if you're standing on your street and your street is flooded. There's not many images of that. We did get some, for example, from Wikipedia and kind of these Pixabay, things like that, free image sites. But then we also had one of our collaborators create a virtual world. Essentially, you can see images here that enabled us to play with the level of the flooding, to explore all different angles, to explore different scenes like suburban, urban, rural areas, and generate images that are pretty realistic. And so we created the simulated data set of almost 3,000 images from this world, and we could try to tune the different parameters to make sure we had enough data. And our real data set is around 1,000 images, I think, so not very much. And so generative adversarial networks, in a nutshell, are a branch of machine learning algorithms that can create new content. So it can be images, it can be videos, it can be sounds. Actually, it can be text. So the idea is that based on some data that you give the network, it will learn what constitutes, for example, human faces, and it can generate new ones that it hasn't seen before, that don't exist actually. And so these two images are taken from a website called This Person Does Not Exist. And as you can see, they're very, very realistic. So increasingly and disturbingly sometimes. And on the bottom, you see what's called conditional GANs. And essentially, it's a way of transforming an image or a video into another domain or another category. And so it can be used for different applications. Like, for example, you can take a photograph and transform it as if Monet had drawn it to make it an impressionist painting, for example, like of a, I don't know, New York skyline or London skyline, which Monet never saw. Or you could do it, for example, transforming a horse to a zebra. And as you can see that the network even transforms the grass to a kind of a drier savanna type grass, because it learned that zebras are often seen in the savanna, and it can do it in real time or in almost real time. But as you see, there are some artifacts, like, I don't know if you noticed, but the zebra's tail is striped, which is not the case for real zebras. So, we've gotten into a pretty decent amount of realism with GANs, but there's still some quirks that are pretty funny. And so I won't go over in this in too much detail, but essentially this is the high-level architecture of what we call the masker from our generative approach. So it takes an image and it essentially will generate a mask based on all sorts of losses and features, etc., using both real and simulated data in order to kind of take the image, and then we figure out essentially what are the categories on the image, like buildings and ground and sky, et cetera, and then based on other images it's seen of flooding, it will kind of imagine where a flood would be if it was in this image. And so essentially it's a lot of tweaking, a lot of kind of a lot of decoding and encoding. We use cross entropy and minimum entropy and things like that. But essentially the idea is based on pairs of, for example, from our simulated world, we have pairs of images like normal and flooded. It will learn where floods typically go. And then we have a painter architecture that takes this input mask that's just going to be empty, or here it's gray. And based on images of water and images of floods, is going to generate water texture on the mask. And so the reason for this is because we realized that so flooding is essentially just destructive in the sense that you don't really see what's under it. And so we figured out that we can just give the painter, what we call the painter, the rest of the image, and it's going to draw water, generate water in a way that's actually contextual based on the color of the sky or the building, etc. So this is also based on an architecture called Spade, which is really interesting. If you can actually go and check out their demo. They have it's NVIDIA's Spade architecture, and essentially it allows you to, for example, draw a landscape. Essentially, you will like draw the ground in brown, draw a tree in green, just like very broad strokes, draw the sky in blue. And it's going to generate a realistic image based on these kind of, like it's like a Windows Paint program. You'll just draw like these basic shapes and colors, and it's going to generate a realistic landscape that you can actually also change like the warmth, the color, the sun, etc. So we're kind of inspired by this approach. We modified it a little bit because our application is different, but typically it's these kinds of, they're called res blocks, these kind of big blocks that will generate a really realistic looking texture. And so in results, like, for example, this is a type of image that we'll see. I kind of cut it so it fits on the screen, but typically this is the kind of images that we'll have as input images. So kind of people entering their address and having a house. Then our masker will say, okay, well, the water will go here. And as you can see, it's actually pretty good at making the water flat and kind of going around buildings and making, for example, as you see along the garage, it makes a flat line and then it goes around the house. So it's actually pretty good. And then the painter will generate the water. So as you see, it'll take into account contextual elements. The garage is a bit beige and the house is a bit green reddish. And so this is kind of the types of results that we get, which are pretty good. Same thing with kind of a street level perspective. It generates the mask and then it generates the water. And as you can see, this water is a lot more kind of blue-gray compared to this water, which is more green. So it actually, because it's a non-deterministic algorithm, it can generate different textures depending on the elements around it. And full disclosure, GANs are kind of black magic at this point, so I couldn't tell you exactly why this is like more blue or more green. But the idea is that it does take the sky and the houses into consideration when it generates the textures. So other events that we've been working on more recently. So flooding actually took us like a year to figure out, more than a year. Now we're working on smog, so which is also kind of a less extreme, I guess, less destructive event, but very, very common, increasingly common. And what we're using for this are depth maps. So there's actually existing algorithms that have been pre-trained in order to estimate depth of images. Essentially, there's one called mega depth. There's plenty, and essentially we modified these algorithms in order to for city scenes. And so essentially we take an input image, we compute its depth map, transmission, then we scale it because we essentially want to make it less light because smog actually blocks out the sunlight. Then we compute irradiance essentially by we have a set parameter that we want to achieve, and then we generate this kind of output image that will take into account and will generate more smog closer to the camera and less smog further away, and to create this kind of depth effect while taking into account the scaling and the objects. And so as you can see, this works pretty well. This is kind of a more recent phenomenon that we're working on, so it's not quite as flashy as floods, but still we're playing around with different parameters and different approaches in order to make kind of these, and also different colors, because the color of smog depends on the type of particle, and so in some cases it could be more coal power plants. In other cases it could be for example, industrial factories and things like that. So we're also trying to have like a random seed that will assign a color to the smog as well. So these are kind of work in progress. Also, wildfire is something that we're working on. Initially, we wanted to represent wildfire, but we were always kind of hesitant because we didn't want to show people's houses on fire, and we didn't want to show people's houses burned down because that's kind of not the point. And then the images of the California wildfire came out a few months ago, and then we realized that actually the biggest impact is kind of this red sky effect. I don't know if you saw them, but you have like normal streets that are very dark and the sky is completely red. And this was even like 50 kilometers or from the wildfire itself. So essentially this is what we're aiming to replicate. So we're also using kind of, instead of depth maps, we're using semantic segmentation to figure out where the sky is. So take an input image, we make it a bit more contrasted, darken it, and then when we segment the sky, and then we add a Gaussian blur in order to have this kind of depth effect as well. And then we're also playing around with different color seeds and things like that in order to have, because sometimes it's more orange and sometimes it's more red. So this is kind of also quite preliminary results. But overall, I think what we're going to settle on is we're going to have these 3 extreme climate events on our website. And actually we're working with a development agency to create our website now. And essentially like the idea is like, what would it look like if it happened in your own backyard? So we're going to start with real events like flooding in Bangladesh, like a wildfire in Australia or California. And so the idea is we're going to help people learn about climate change, what causes flooding, what are the different impacts it can have, what are the mechanisms behind it, and then enter an address of their choice and then see what would it look like. What would the Australian wildfire look like if it happened in Montreal? What would the flooding in Bangladesh happen what would it look like if it happened in Sheffield? So the idea is really to help people empathize, and then we're going to have kind of actions that they can take to reduce their carbon footprint and to learn more. So this is kind of a bit of a different machine learning project in the sense of that it's really an educational tool. The idea is, I guess there's some fundamental research involved, and actually GANs have turned out to be pretty tricky, but the overall goal is kind of awareness raising and education. And so the final project that I wanted to present to you is kind of this, I call it my side hustle, because so I was working in NLP before, and I really like working with text. And but most of my time is spent with GANs. And so about a year ago, I got kind of frustrated, and I said I wanted to do more NLP research. And then so Joshua, my supervisor, said, go ahead. And I recruited a few students to help me on this project that we called Climate QA. And the motivation behind the project is that, so climate change inevitably is going to have a massive impact on the stock market. It's estimated to be in the trillions of dollars, but it's really hard to know when that's going to happen. And when I was working in finance, there were a lot of people who were trying to figure out, how stocks, how global assets will be impacted by climate change, and then how to estimate this risk. How do you factor in, for example, a real estate company that has coastal real estate? How do you factor in climate risk into, for example, its evaluation or its stock price? But there's actually very, very little quantitative data on the subject. And the data that does exist is kind of buried in pages and pages of kind of financial reports and kind of this really boilerplate language. And so for a 50 or 100-page report, you're going to have a few paragraphs that are actually relevant, but you can't. It's very hard to just control F climate change, because they're going to be talking about different things like greenhouse gases, like I don't know. Sometimes it's going to be like about physical risk. Sometimes it's going to be about commercial risk, legislative risk. So there's all these different types, and so essentially right now it's done by hand, and it would be really great if it could be done a bit more seamlessly. And so actually there are initiatives to make it more structured, to make climate disclosures, as they call it, more structured. And so there's an organization called the TCFD, or the Task Force on Climate-Related Financial Disclosures, that was founded essentially to help people make these voluntary climate disclosures, which mostly are voluntary, but actually increasingly mandatory in some countries. So some countries are really saying that companies have to disclose climate risk. They don't have a choice. But still, it's very heterogeneous, and it's really hard to analyze. But they essentially released a set of 14 questions recently that will aim to guide sustainability reporting. So this is what analysts use when they're analyzing these reports. They'll have the 14 TCFD questions, and then they'll try to find the answers in the text. And essentially, for an NLP researcher, we're like, oh, question answering. This is question answering. And so essentially, we reached out to the TCFD. They gave us some label data from past years, and then they said essentially how try to train a model that will help us. And so that's what we did. And so we adopted a transformer-based approach because I don't know if you've familiar with recent kind of progress in NLP, transformers have been used in a lot of applications, natural language inference, question answering, what have you, machine translation. So transformers are kind of these big machine learning models that can crunch a lot of text. And so we had a very small set of documents actually that were hand labeled, and we decided to frame this as a question answering tasks. And we tried different architectures, and finally we settled on one called ROBERTa. And so BERT is kind of the first transformer one. And ROBERTa is a subsequent version of BERT. And after that, there was ELMO. After that, there was, well, for example, GPT-3 is also kind of a transformer-based architecture. So we took ROBERTa because it was a kind of more efficient and smaller, and decided to train it on this data set. And ROBERTa, generally speaking, has a two-step approach. So first, you can pre-train it on unlabeled data, and it will enable the model to learn kind of the language of the data. So in our case, it was financial reports that actually have pretty specific language. It's not going to be just like, it's not going to be the same as Twitter language. It's not going to be the same as just normal kind of colloquial English. It's going to be very formalized financial language. And so we trained ROBERTa. We pre-trained it on some unlabeled documents, and then we fine-tuned it on this small set of questions and answered. And this is the actual task. So the pre-training is kind of this general learning of what constitutes the context. And then after that, you can, when you fine tune, it's actually like a classification task or a prediction task. This is when you actually add the last couple of layers of the network that are the ones that are making the prediction. That's a general kind of procedure. And so yeah, we pre-trained our model on labeled financial reports, and then fine-tuned on the question answer pairs. And so the kinds of questions are kind of broadly speaking things like this. So does the organization describe the targets it uses to manage climate-related risks or opportunities? So for example, targets are reductions in emissions. Targets can be carbon neutrality. Targets can be, I don't know, 10,000 gigatons of carbon emitted. Like these are usually kind of these kind of we are aiming towards. And so, for example, an answer that was labeled by an analyst is, we aim 15% by 2020 is equals targeted reductions in energy and emissions. So these are kind of broad passages that are labeled. And then there's also this kind of very generic Q1. The first question of TCFD is, does the organization describe the climate-related risks and or opportunities the organization has identified? So you see this very broad question. And so it's like, in this answer, it's like all of the company's raw materials are agricultural commodities, and et cetera, and they are subject to factors such as changes in weather conditions planning, changes in global demand, et cetera, et cetera. So as you can see, these are very, very vague answers in most of them, but they're already something. It's already a way of figuring out how companies are exposed to climate change. So we had around 300 labeled reports with the 14 questions. That was our labeled training data. And these are the results by sector. So we've got agriculture, energy, banks, transportation, insurance, materials, and buildings. And what we were looking at is, so to take a step back in machine learning, typically what we do is we have a training set that we train on, and then we have a validation set, which is what we use to kind of track our progress. And so we keep, training your model, tweaking some parameters, testing on the validation set or validating on the validation set, et cetera, until you get a performance that kind of makes sense to you. And then you typically, if you can, have a hidden test set that your model has never seen before. And once you've settled on an architecture, once you've settled on a set of parameters, essentially you don't want the model to see this at the very end. You'll test on the test set. And that is essentially, for example, new reports. In our case, it was companies that were never seen before and from the same sector. So the idea was, the model couldn't have learned this, couldn't have memorized this data. This is completely new data. And so what we were comparing is the difference between this validation score, which is kind of like the perfect score that you get when you're optimizing towards that particular set, and the test score, that it's a completely it's essentially a completely new report that it had never seen before from another company that has its own kind of jargon and its own way of disclosing things. So what we were really interested in was minimizing the difference between validation and set, because this is essentially kind of the main goal of machine learning is to be able to generalize. So we really wanted our model to be able to generalize to new reports and new companies. So as you can see, it was mixed results, but overall the generalization capability of the network was around 10%. So on a completely new report, it would have done an average 10% worse than on the reports that it has seen that it was validated on. And for some sectors, it was better. So for example, in energy and in banking, typically it's kind of the same types of disclosures. I'm pretty sure they just copy paste this stuff. So, the model learned what constitutes an energy or banking disclosure. For other sectors like materials and buildings or agricultural and food, there was a bigger test difference. But because, for example, even in agriculture, food and forest, there's like a lot of different disclosures that can be done from, farming to logging. So these are completely different types of risks and types of opportunities. So obviously when a new one comes along, it's harder to generalize. But overall, we had a validation score of around 92, test score of around 82%, and the difference was 10%. So we're pretty happy. But our goal was always to create an actual tool that people can use, not just a machine learning model that we kind of published about and forgot. So right now, what we're working on is deploying this climate QA model, as we call it, using Microsoft Azure. So to actually host the model on the cloud and to create a user interface, this is where we're at right now, to create a user interface where someone can essentially drag and drop a PDF with absolutely no knowledge of machine learning or any kind of technical skills. And then we will extract the text from that PDF, run it passage-wise through the model, and then print out essentially a list of relevant passages to TCFD questions in HTML format, so just someone can just open up in a browser and read through it. And we'll also let people choose the questions they're interested in, and maybe we're thinking of also having a threshold of confidence so that there's not too many passages that get returned. But generally speaking, I mean, we're almost there. It's a bit of an uphill battle because we're not computer developers, we're machine learning researchers, but essentially, hopefully in the next month or so, we're going to have a climate QA website where anyone can essentially drop a document and get some results. So the conclusion, I guess, for me is that no matter what your area of skills or expertise is in technology or machine learning, it's possible, and it's actually pretty straightforward to put them in use in the fight against climate change. So, and also that there's so many things that can be done. It's really like this large spectrum of solutions, of problems that need solutions. So there's no single one. And I think that's essentially what can make people feel kind of overwhelmed, is that there's so many things that need to be done in order to move the needle against climate change. And so people have trouble choosing. People think that, there's nothing that I can do for climate change because it's just so much bigger than me. But actually, once you start learning more and working with domain experts who have been working on these problems for a while, you realize that there are a lot of things, and sometimes relatively simple things, that can be done with data and machine learning that can really help. And so I'm not techno optimist to the point of saying that AI is the solution. So it's no silver bullet, but it's definitely a piece of the puzzle. And I think that there's a lot of things that it can be used for to complement existing endeavors, especially. So in writing our paper, we realized that machine learning practitioners, researchers have this kind of have a reputation of thinking they can solve everyone's problems with machine learning. And so we're trying to avoid that at all costs and essentially stay open to people who have been working on this for decades, essentially, and to just use our skills and use our experience to find these specific points where AI can be used to make a difference without trying to reinvent the wheel or redefine whole areas that have existed for decades. So I think that connecting with domain specialists and connecting to people who have been thinking about this for a really long time is really important. And that's what we've been trying to do in all of our projects. We've always been trying to include stakeholders and experts in order to make AI part of the solution, but not the only part. So thanks. I think that was pretty much 45 minutes. So if you have any questions, I'm open.
All right. Thanks, Sasha. Sorry, I was just trying to unmute and took a while. But thanks a ton. This was very clear and very, very pointed examples of, as you mentioned, we can get lost on what needs to be done. And these are some very clear examples of, how you can focus and work on very specific areas. So we have one question I'm going to ask Danae. Can you come on screen? I'm just inviting you if you want. If not, I can ask for you as well. I'm just inviting her. Hopefully, she can join us. Okay, maybe not. So I can ask for her then. So she's asked, how do you combine the latitude, longitude, and date information? Given that the ResNet output vector is considerably big, do you map these features to a bigger vector?
No, essentially we encode them. I mean, we don't map them together with the image. I think that's the question. So the image goes through the ResNet, and then it gets combined with the lat long, and so the lat long are encoded separately, not together. And then when they're combined, we have the probability redistribution.
Right. So that's it. So others also, if you have any questions, please feel free to ask. I can ask maybe in the meanwhile about your when you showed the flooding and so on. I'm not sure if I understood, but do you also link it like to a climate model and what the prediction of the amount of flooding or the probability of fire is, and then
no, what we do is we link it to existing events and kind of global probabilities, but it's really hard to essentially climate models are very global by definition, and so it would be hard to do it for a specific place. So it's an open question, essentially. For example, your specific neighborhood or your specific city, how liable it is to get flooded, because coastal flooding is relatively well, I mean, it's kind of understood. It's better understood, but inland flooding, like from rivers and snowmelt and things like that, is very, very difficult to model. So, for example, here in Montreal, we've had flash floods in springtime in the last couple of years because of snowmelt, and essentially no one had predicted them. It was because there was like a spike in temperature all of a sudden, for example, in February or March over like a day or two, and all of a sudden all of the snow melted and it kind of flooded places that were never flooded before. And so these kinds of phenomena are really, really hard to predict, because essentially it's hard to predict what the temperature is going to be like on February 5th, 2030. That's a kind of a very difficult prediction. So essentially we consulted with climate specialists, and they said, like, we can't have the models. We can have a global model for you, but it's going to be way too high level. And so currently the approach that we're taking is kind of a global approach, saying that floods globally are becoming more frequent on kind of a planetary scale. But it's without like drilling down to the specific place people are at.
Cool. So maybe I can ask another question. This is again related to the bigger picture. So this is, it's also close to my heart to work on something like this, but it's really difficult to identify. As you said, you can feel lost, and you're part of this paper on tackling climate change with machine learning, and of course one goes through that. But even there, one gets lost, and there is also the website climatechange.ai. So how do you really identify, this one question? Finding data sets is not easy. If you search for collaborators, you don't know whom to ask. And if you ask, you don't know what to ask. And then they may not be sure how this can fit in. And in the end, you don't even know what kind of impact this will have in any case. So how do you proceed in such a...
So there's several questions, I guess, in your question. We're working on curating data sets and resources. Actually, hopefully, we're going to release a climate change AI wiki in the next month. So we're going to have the sections in our paper, and within each section, data sets and resources, background readings, conferences and workshops, et cetera, et cetera. We're going to have different sections, and we're going to have also kind of action directions that can be taken. So for example, within electricity systems, you can work on nowcasting. And then within these specific domain applications, we're going to have links to people who work on it, organizations, and hopefully the idea is we're going to share with our network. So people start, it's going to be kind of a directory of people who are working on these things. And in terms of choosing a problem, I think that, I mean, it's kind of it's a personal thing. I mean, some people are, I think that's why it's interesting to go through the website, because you'll discover new things, and then maybe you'll see that you're really interested in transportation or agriculture or whatever. Like you'll see as an expert of machine learning where you can contribute to this. So I think that's kind of a very hard to answer in someone's shoes, this question. And for estimating impacts, it's actually really hard to estimate, I mean, to exactly quantify in tons of carbon or tons of greenhouse gases the impacts of most of the projects, because it's first of all, there's very little data. I mean, for example, you can say that, okay, electricity is roughly a third of global greenhouse gas emissions. But you say you're working on a project in solar forecasting, and essentially if your project works and people start using it, you can have some reduction in this number, but it's not tangible from upfront, essentially. So for example, we had someone come present at one of the climate change AI workshops who was working on a way of using reinforcement learning to reduce the greenhouse gas emissions of commercial flights, and essentially by calibrating the plane and the wind speed and things like that, they said that they could reduce emissions of a flight by 2 to 3%, which is actually massive. But when you think about it, people have to adopt it, right? Plane companies, airlines have to start using it. It has to be compatible with all the types of planes. It has to be compatible with the autopilot. It has to be, like, there's so many conditions, so that even if you multiply that 2 to 3% by the global emissions of the airline industry, it's not going to be, that's like the maximum boundary, but the minimum boundary is hard to define. So this is something that I've always grappled with, like what's the most impactful project that one can work on? And I think that there's no solution, no silver bullet to that question as well.
Cool, thanks. So we have another question from Soumya. I've invited.
Yep.
Yeah. Can you?
Hi.
Yeah, ask, yes.
Hi.
Hi, Sasha. Thanks for the great presentation. I had written the question down, so I'm going to read it almost ad verbatim. Would you say that the presentation, because this feature that you're going to provide with Google Map, it's aimed at individuals. So would you say that this presentation of this negative events at times can be a bit overwhelming? And are you also thinking of suggesting some actions that people can take to, mitigate these sort of events? So like on the side, potentially showing that, this flooding can be reduced if you try and reduce your digital footprint, your carbon footprint in this particular manner. And these things have shown this sort of improvement in the past. And, I understand it's a bit complicated, right? Because it involves a certain amount of causal reasoning, but even without the direct causal links, are you thinking of providing some sort of action-based suggestions?
Definitely. We're going to have, I think the culmination is when you see the image that you request, you're going to have a button which is Act Now. And essentially we're going to have a list of actions that can be taken. The problem is that most of the quantification of the impact of these actions is on a planetary scale. So we kind of have a general idea of what would happen if everybody went vegan, for example. Right. But it's really hard to say what would happen if I went vegan or you went vegan. So it's really hard to do this on an individual level. And this is kind of also part of the enigma, is that it's a tragedy of the commons, climate change, is that everyone needs to make an impact. So we're going to have these actions. We're very hesitant about actually mapping kind of impacts to these actions, because it's just a very general figure. And I mean, there have been projects like Project Drawdown, for example, that is exactly. So I mean, we can link to projects like Project Drawdown, but even then they're very kind of these are global solutions, right? Like going vegan, stuff like that.
I see. Right, and they may also sometimes be a bit controversial. So I guess you'll have to ask the people, do you want to hear some suggestions? And if they say yes, then you have to
Yeah, we were
Okay.
also debating whether we will include like write to your representative, for example, things like that. Like write a letter to your representative saying that climate change is important to you. Or
Right.
actually something that we're playing around with, I think that we'll actually do is kind of a time capsule idea. So for people who want to, that they can leave their email, for example, and then to receive an email in 1 month or 3 months to say, have you taken action? And
Right.
like eventually have some kind of newsletter or something, just so people can follow up, because essentially, if somebody just forgets about this, then we didn't really achieve our purpose. The idea is to be able to have some kind of a retro action and to have a feedback loop, essentially.
I see. Interesting. Thank you
If you
so
have any
much.
other ideas of things that we can include, we're open. This is what we're working on right now.
Sure, I can write to you. Great. Thanks.
Yeah, and actually, so we're working with a behavioral scientist in Montreal who is doing a study with our images. It's pretty exciting, actually. So he's comparing different groups. So he's going to have 3 experimental groups. One group that will receive a text about essentially how extreme climate events are getting more frequent. The second group will receive the same text plus kind of a generic image of a flood. And the third group will receive one of our images of their house or the address that they enter. And he's going to compare after that their answers on questions about perception of climate risk. Are you more likely to change your habits? Are you more likely to travel less and things like that? So the idea is, if given, I think he's going to have like several thousand people per category, and to measure whether the climate risk gets impacted or not.
Very
more
interesting.
Yeah, hopefully this will really validate our approach.
Yeah, really cool.
Great. Thanks, Sasha. And I guess we have no more questions. So I guess we can break. Thanks again, Sasha, for this wonderful talk. And hopefully we'll be in touch. And some claps from my side and from the chat box as well, virtually. So
Thanks,
again.
everyone.
Cheers.
Bye.
Goodbye.